Okay, class, this is the video about limits involving infinity. First thing we're going to look at is the graph of f of x is equal to 1 over x. So if you guys remember what that looks like, it has a vertical asymptote at x equals 0 and a horizontal, well, we'll talk about where the horizontal asymptote is in a second, but it looks something like this if you graph that on your calculator. Now, hopefully you guys observe that the limit as x goes to positive infinity of the function is approaching 0. And also that when you look to the left and approaching negative infinity, it's also going to 0. Which means that we have a horizontal asymptote of y equals 0. Which we should have remembered back before because of we learned horizontal asymptote rules, and if x is heavier on the bottom or a bigger power on the bottom, it automatically goes to 0 for that piece. So what does that mean? It means that y equals b is a horizontal asymptote if either, so it only needs to be one or the other, the limit as x goes to infinity of a function is equal to that letter b, or the going to the left is equal to b. If either of those things happen, if it approaches a constant, then you have a horizontal asymptote. You can have two in a problem, actually. Okay, so now we're going to we're going to use our limit properties to find the limit of this and identify all horizontal asymptotes. So we want both of them. I'm going to start with the x going to positive infinity of 2 plus 1 over x. And what we can do is use limit properties to break this apart. And when we do that, you should note that the limit as you go to infinity of 2 will just stay 2. And the limit as you go to infinity of 1 over x, we already talked about this goes to 0. So that means the limit as it goes off to the right is 2. If you do it with the left, you get the same thing, because when you break this apart, it doesn't matter if it's going left or right. You still get 2 and 0 and 2. So since they're both constants, but they're both the same constant, the only horizontal asymptote we have here is y equals 2. Okay. Now we're going to find out what the limit of sine of x over x is as it approaches infinity, as the x approaches infinity. And we're going to use our sandwich theorem to do that. So we know again that the trig function sine of x goes between negative 1 and 1. I want to make it look like this, so I divide everything by x. So I have negative 1 over x is less than or equal to sine x over x, which is less than or equal to 1 over x. Now I just take the limit of both the endpoints, or both of the end restrictions of those functions. The limit as x approaches infinity of 1 over x, negative 1 over x. Again, it doesn't matter that it's negative. It will approach 0. And the limit as x approaches infinity of 1 over x, we've already talked about a bunch of times today, is 0. Therefore, the limit as x approaches infinity of the function sine x over x is equal to 0. And this is something you have to kind of know, kind of like knowing that the limit as x approaches 0 of sine of x over x is equal to 1. Now we can use this to help us out. Find the limit as x goes to infinity. Okay, we split it apart. And we have 5x over x, which will cancel, plus the limit as x goes to infinity of sine of x over x. So these cancel, so it's really just the limit as x goes to infinity of 5, which is just 5, plus the limit as x goes to infinity of sine of x over x. We already just found this, and we know that that is 0. So the limit is 5. Okay. Next, infinite limits as x approaches a. Okay, we're going to look at this function first. This is basically a vertical asymptote. Okay. As you approach a vertical asymptote, think of it as approaching a wall. You're not going to run into the wall, so you're going to make a quick turn up or down. Okay. So if we look at this and approach, as x approaches 0 from the right, this is going to go up forever and ever and ever and ever in the positive direction. So we would say this is approaching infinity, and as you come from the left, it's going down forever and ever and ever, and we would call that negative infinity. Okay, so what happens at a vertical asymptote? Well, x equals a is a vertical asymptote if either the limit as x approaches a from the right is equal to some sort of infinity, or the limit as x approaches a from the left of the function is equal to one or the other infinity. It's not going to be both, but it could be negative or positive depending on the problem. So let's look at what that means for this problem here. Find the limit as you're approaching 3 from the right of this and from the left. Well, first thing you look at is you plug, we used to just plug 3 in to see what the limit was, but you get a 0 on the bottom. Okay. Then you look always to see if you can cancel something. And you can't factor anything on the top. So you're stuck there. So really you just look at the bottom now and go, wait a minute, if nothing cancels, this has to be a vertical asymptote, just remembering our properties of rational functions. So if this is a vertical asymptote, pretend there's a wall at 3. And we want to know, how is the graph approaching this wall? Well, the answer is going to either be infinity or negative infinity. Okay? So right away, we know it's going to be some infinity. So all you have to do is kind of figure out which one it is. So it's going to be an infinity. So let's be careful though. I just have to see if I have to put a negative sign in here. From the right. From the right means we're coming from values higher than 3. So if I put like 4 in, you just have to check, is it going to be positive or negative? And if I put 4 minus 3, you get a positive on the bottom. And if I put a 4 in here, you get a positive on top. So the answer is positive infinity. It'll look something like this. From the left, you put a value in lower than 3. So for example, put 2 in. At 2, you get a negative on the bottom, and you get a positive on top. Therefore, the limit of this function is going to be negative infinity when it approaches from this direction. Okay. All right. Finally, we're going to talk about end behavior model. End behavior model. Okay, it's basically how the graph behaves as it goes to plus or minus infinity. Now, end behavior model has basically been our horizontal asymptotes from before for rational functions. But we can actually expand on this idea when it's not a horizontal asymptote. So we will still use our properties though for functions like number 5, because number 5 is a rational function. So we would look at the top and bottom, and when you look at these, you always look at the highest degree on both the top and the bottom, because those are the things that are determining what's really happening for big values of x. Everything else doesn't really matter. It's not affecting it as much. So if you look at this, you just get 2x to the 5th over 3x squared. If you simplify this, you get 2/3 x to the 3rd. This is your end behavior model. So we'd say y is equal to 2/3 x cubed, which means that as the graph gets really, really big in both the left and the right directions for this one, it will follow this function. Okay, it can do a lot of weird things in the middle, but so for example, if this is my function, that's my function. I know that's not really what it is, but this function here looks something like this. So at the end of this graph, whatever it is, it'll look like that. Okay, so that's finding the end behavior model when it's a rational function, but sometimes we get ones that are not rational functions and we have to think about them. The way I think about these is if I go really far to the right, which one wins out? Which one overpowers the other one? Because that's the one that's it's going to go to for its function. So going towards the right, so the right one, the right end behavior model, is when we are putting in about where x is going to infinity. So let's look at what happens when x goes to infinity. This piece will go to infinity. Okay, which is pretty powerful. That means that that's going to keep going up by the numbers. But we also have an exponential function, and those usually actually go up faster, so sometimes that one wins out. But let's see what happens when we put in an infinity here. This stays negative, which basically means it flips. So I have an infinity here plus 1 over e to infinity, if you want to call it that. When this gets huge, anything like that, it means that this piece goes to 0 because it's 1 over a really big number. So as you go off to the right, this keeps getting closer to 0 and is not affecting the problem at all, and this keeps going up to infinity. So we'd say the right end behavior model is f of x is equal to x, because that is the one that is winning out in this scenario. Now let's look at the left one. That's when x is going to negative infinity. Okay? So as x goes to negative infinity, x is kind of still doing what it's doing, just it's negative infinity, plus e now is negative infinity or positive infinity. So as it goes to the left, this one gets bigger, but this one gets bigger too, and this one gets bigger faster because it's an exponential. E to, like, if I said e to 100 minus 100, if x was 100 for example, or x was negative 100, it would just be e to the positive 100, which is a very big number, and then we'd be taking 100 off of that. Okay, so eventually as you keep going to infinity, this number is going to be so much bigger than just the negative infinity. So the left end behavior model is the piece that is the exponential. And that's the one that would win out going to the left because the negative turns to a positive. And that is a right and end behavior model. So I have one extra problem here, kind of just to review some of the things we've been talking about before this section. Just finding a limit at some value. And this kind of reviews also one of our skills we learned last year and the beginning of this year. Again, to find a limit, the first thing you do is plug in. If you plug this in, when you're finding at a value, you get 4 plus 2 minus 6 is a 0 on top. And when you do all this, negative 46, this becomes 20 and 24, 44, 46. You get a 0. So when that happens, the next step is you need to try to simplify to cancel out maybe a whole. However, to simplify something, you need to factor it. The top factors easily. The bottom, however, does not. Remember, when you have something that's bigger than a quadratic and you can't figure out how to factor it, you need to find a 0 and then synthetically divide. Now some of you guys might be wondering, well, how do I find a 0? Because we used to use our calculators for that, and if this is a non-calculator problem, we have a problem. But we actually don't, because you actually, believe it or not, have a 0. What made the bottom 0 already? It happens to be this value that x is going to. We know that when x is at 2, there's a 0 there. So we can use that information to synthetically divide by 2. and then break it down. So we have 3, 5, negative 23, and 2. So you, to synthetically divide, bring the number down, multiply, and then add, and then multiply, and then add, and then multiply, and then add. And sure enough, you did get a remainder of 0. So here's what happens to this. This turns into the limit as x goes to 2 of, shouldn't put an equal sign there, of the top becomes x minus 2 and x plus 3. And the bottom factors out to, well, if we divide it by 2, that's the factor x minus 2. And we're left with 3x squared plus 11x minus 1. So now we can actually do this problem. These cancel. There's a hole in the graph there, which is okay for limits. We plug in 2, so we get 2 plus 3 is 5 over so we get 5 over 21 plus, what is that, 12? 33. And that's the limit. That's what the graph is approaching, or the function's approaching in the y as x approaches 2. Good. All right. That was just kind of a review.